Well, hello, once again. Greetings from Northern Michigan. It's time for another episode of Flat Earth Can't Science. I'm your host, Bob Townsend, and today we're going to take on one of my favorite flat Earth scientists, Phuket Word. Phuket Word has dozens, if not hundreds, of videos out on the web putting forward his special version of perspective. In fact, he recently put out a 1 hour long documentary on perspective and navigation in the real world. That video was so special it's probably going to result in several shows of Flat Earth Can't Science, but today we're going to start off with his version of how a sextant works on the flat Earth. So pop some corn, grab a drink, and prepare to be amazed. Lord knows I was. So today's experiment is going to be how to use a sextant on a flat Earth. Okay, so here's what we have. Phuket Word went to Wiki and read about a sextant and how it worked on a spherical Earth. Not to be outdone, he had to figure out some way that it would work on a flat Earth as well. After briefly amazing us with his extensive knowledge of right triangles, he was able to determine a height for the star Polaris. He then continued on to show how we could get sextant readings on a flat Earth, but quickly ran into trouble, which he conveniently got out of by, you guessed it, perspective. Now, the logical fallacy in play here is what's called an argument from ignorance. You see something, you don't know what it is, so then you make up a story as to what you think it is, and then call it good. Examples of this include UFOs. The U, of course, stands for unidentified, and that's the end of the story, but we attribute them to alien civilizations. Similarly, we could say we see something in the woods, we have no idea what it is, so therefore it must be Bigfoot. In the case at hand, Phuket Word clearly has no idea of how to do navigation or use a sextant, but that doesn't stop him. He'll figure out a way to make it work. Well, for those of you unfamiliar with what a sextant is, here's a quick tutorial. Basically, what you're doing is you have a telescope with a semi-glazed mirror in front of you. You line up a star in the sky with the horizon and read off the elevation angle. On the globe, the real world, that angle of declination is your degree of latitude. Let's let Phuket Word explain this to you in his own words.
This is an instructional video that will explain how to use a sextant observing Polaris to determine your latitude. And of course it assumes a globe Earth model. But in fact you can also assume a flat Earth and it works perfectly fine in exactly the same way. Okay, so it doesn't matter how high in the sky or how far away Polaris actually is from the North Pole, above the North Pole. What matters is how far away you are from it. So if Polaris is local and you get further and further away, it's going to appear to sink to the horizon, and this will determine your latitudes. The latitude lines on the Earth, flat or round, are determined, or were determined, by the position of Polaris above the horizon. On the globe model, you assume the Earth's surface is curved. On a flat Earth, you incorporate the reality of perspective.
And you want to see Polaris, you're going to look straight up over your head. So if we measure the angle that's formed between the surface of the Earth and straight up over your head, well, it's a right angle. It's a 90-degree angle. Well, the latitude of the North Pole is 90 degrees north.
Okay, so that's fairly straightforward, straight up towards Polaris. And again, we've assumed that the surface is flat and the horizon that you're looking across is also flat, perpendicular, so you get the 90 degrees. So, of course, the latitude lines of the Earth go down, 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 90, 80, 70, 60, 50, 40, 30, down to 0 at the equator. And then, of course, it starts again. And, of course, it's assumed that it is the curvature of the Earth that blocks your view of Polaris. When, in fact, we know that across a flat plane, if Polaris is very local, then, of course, you'd get exactly the same optical effect.
If you were to travel a little bit to the south, let's say you were located over here, well, now we can see that here's the horizon, Here's the surface of the Earth. If you want to see Polaris, you're not going to look straight up over your head. You're going to look this way. And so there's a much smaller angle. Maybe that's around 45 degrees. So maybe.
Okay, so again, they have to assume a flat surface, a flat horizon at the observer's eye level, despite this curve. So they're not making an angle that leads directly to Polaris. They are making an angle that goes from the observer's horizon, their eye level, and then up to where Polaris is apparently visible, which is here along this line of sight. So the difference here really is the angle of perspective, or that angle of declination that you would get across a flat surface, rather than assuming that you see the star here even though it's physically supposed to be there. So you're getting the same declination that we see due to perspective.
Maybe your latitude is 45 degrees north. If you continue going south, let's say you go to the equator. Well, the horizon, or the surface of the Earth, is right over here. Straight up over your head would be over here, so Polaris is clearly not over your head. Well, Polaris is basically the same direction as the horizon. So in other words, there's no angle. It's 0 degrees.
Here's another illustration that clearly shows the contradictions that have to be made if you assume that you're on a curved surface. Again, we have this line of sight, the eye level horizon, as the starting point for measuring the angle up to Polaris, which, although is a speck of light that is supposed to be physically placed above the North Pole, it appears for this person here to be up here, and for this person over here to be up here. These are thousands of miles apart or distant from the North Pole.
The reason the Phuket word is mystified here is that he just fails to comprehend the distances involved. Polaris is some 400 light years from Earth, and by the time light from that star arrives here, it arrives in parallel rays. Although you can clearly see it illustrated here, it is just beyond his comprehension. Now let's completely switch gears as he goes on to talk about 45-degree right triangles.
We know that when we have a triangle like this, so we create a triangle with an observation. If we look directly up at something, or this side here of the triangle, the vertical side, can represent the height of a tree or a tower or something above the Earth. And if we have a distance across the flat surface that is equal to this height with this right angle here, we then have an angle here of 45 degrees. So this is when we can use surveying and trigonometry to estimate or calculate the height of something above the surface based on this side, this vertical side, and this horizontal side being the same length and giving us an angle of 45 degrees right here. Once you get further away, or you make this triangle longer, sleeker, then this angle changes, of course. So it's after that 45 degrees that is important and where perspective kicks in. And again, if he is at the same distance from the tree as the tree is high, we have a right angle here and a line of sight to the observer. Okay, so what we then get is a 90-degree angle here and two 45-degree angles here. And we know then that the distance between the observer and the tree is the same as the height of the tree. So this is the very simple way we can work out the height of something without actually climbing up the tree and physically measuring it with a tape measure. Okay.
You know, I'm sorry, but I'm going to jump back in here for a second. What he has just described is measurements according to parallax. And parallax is precisely how we knew Polaris was 400 light years from Earth. Carry on, Phuket.
But we can see here that the simple fact that something is further away makes it appear much closer to the horizon or shorter, perspective, angular size, whatever you want to call it.
Okay, so before we go on and start talking about magic pixie dust of silly pseudo flat earth perspective, I think I should probably mention a few things about real perspective. Now, I am going to have a full video on this later, but this is just a little taste. So he mentioned angular size, and I want to actually talk about that a little bit. This is a mil-dot scope on a rifle. Now, the reason this has little dots on it is those dots, the large dots, represent 1 yard at 1,000 yards. So an average 6-foot tall person would be 2 dots tall. So as somebody gets closer to you than 1,000 yards, they'll start growing in your scope. Now this gentleman is 6 foot tall and he is 4 mil dots high. That means that he is at a range of 500 yards. The basic formula is that you take the size they should be at 1,000 yards over the size they actually appear in the scope and multiply it by 1,000 yards. If he was, say, 3 dots high, he would be at 667 yards. We see why this occurs when we start looking at perspective. The easiest way to draw lines of perspective is take the entire width of or height of an object and then draw a line connecting each point on that object to a vanishing point in the distance. Now, as we saw in the last example, if you take an object that is half the distance to the vanishing point from another object, it will be half the size. I think it's very important to also note that it will never be outside the boundaries of the constraints of that triangle of perspective. Understanding this process is the key to understanding why the sun, which is over your head, will never disappear below the horizon, which is one side of that triangle. Now I'm going to go back to Phuket word. I had to listen to this entire hour-long tape a couple of times, so you're going to get a couple more minutes.
So the same tree, again, the tree we know is physically the same height. So if we wanted to represent it at the same height, we could. But here we are representing what the observer sees. Okay, so all of this surface between the observer and the very distant tree now is appearing to rise up to that observer's eye level because of the difference in angular size or perspective. So this is why people who try to debunk the flat earth get confused and get it wrong. They are using the same methodology as is used for the globe earth model and applying it to the flat earth model, for want of a better word, when in fact the globe, as we see here, the curve represents perspective. Okay, so they assume that the sight lines should all cross at the position of Polaris, but they don't on flat earth. Flat earth model is wrong. No, they're confusing. They're trying to use globe earth modeling with the flat earth model. So again, the flat earth is a model of being on a flat plane, making observations that incorporate the reality of perspective. Whereas the globe earth takes the reality of perspective and converts it into a curve beneath our feet. And again, we've got this looking up at Polaris in different positions when Polaris isn't physically in these different positions. They're just telling us that it's because of the light from Polaris spreading so far.
Yep, as you recall, Polaris is some 400 light years away, and when its light arrives at the Earth, it is in parallel rays. That's how I can use a sextant to locate my position on Earth within 100 feet. But I digress. Back to you, Phuket.
This illustration is often used in attempts to debunk the flat Earth, but it's wrong, as it tries to incorporate the modeling method used for the globe into a flat Earth model, but doesn't compensate for perspective, as we saw just now with the trees and the sun. As we get further away from something, it should appear to get closer to the horizon across a flat surface. But here we have all these angles of elevation going to a single point above the flat Earth in this orthographic view, which, okay, may be physically true.
Well, but nothing. It is physically true. This is why a sextant will not work on a flat Earth.
So, in fact, what we do have is a matchup here of 45 degrees latitude and an angle of elevation from the eye level or horizon of the observer to Polaris, 45 degrees at 45 degrees latitude. So we can in fact assume that this may well be correct. The distance from here to here, directly underneath Polaris, would be the same as the height of Polaris above the flat Earth, 4,989 kilometers or 3,100 miles.
Okay, I've had about enough of this, but you heard it here first. Phuket Word has determined the elevation of Polaris to be 3,112 miles above the North Pole. Not 400 light years, 3,112 miles exactly. Well, Phuket, that's really special. Now that I know the height of Polaris above the North Pole, I can actually calculate the angle to Polaris from every degree on the globe from 90 down to the equator. And I've actually done that on a spreadsheet. You can actually download the full spreadsheet. There's a link in the description. In fact, I'd like people to do that just to check my math because I'm not an astronomer and this isn't my field. There may be some of you out there that are better at it than I am. Now what I did was I made note of the fact that Phuket says that at 45 degrees north latitude, the angle to Polaris is 45 degrees. That gives me the height of Polaris, and it allows me to calculate the angle to Polaris that the sextant should read on every degree from the North Pole at 90 north all the way down to the equator, and I've put those in the spreadsheet. I can then very easily calculate the difference between the reading on Phuket's special magic pixie dust flat Earth sextant versus the actual location on the Earth and find out how far it is off. As you can see, as I go from the North Pole down to the equator, my error rate just keeps building and building and building, and by the time I get down to the tropics, I'm 1,500 miles from where I thought I was. But wait, there's more. I love listening to him flounder.
The same thing is done with the sun. Again, this is an attempt to debunk flat Earth by showing that the angles this time, of course, we have the sun above the equator, and we have angles that do not appear to match up in this orthographic view. Again, not compensating for perspective. So, for example, you get, here they've got the equator over here, over here as well. So yes, the sun should be directly above you at the equator, but the further away you get, so here we're going this direction to get to the North Pole, and by then the sun, if you factor in perspective, will be much, much lower, will appear.
But here's the equator here, and then it goes to the North Pole, and then I guess it's over at the other equator, but it's night there, and perspective.
So let's have a look at the kind of results we get when we use this orthographic view and we factor in the reality of the observer's perspective.
Yeah, let's go ahead and do that. Recall that at the North Pole, Polaris is 3,102.3 miles high, according to Phuket Word. So, when you're at the North Pole, it'll be that high. At the equator, we know that we can't see it, so it must be 0. That lets us set up our perspective triangle. Polaris must appear on the top arm of that triangle, going from 0 at the equator to 3,102.2 miles at the North Pole. I went ahead and calculated the angles that Phuket's silly perspective sextant would give me. And I did that for the equator, 15, 30, 45, 60, 75, and 90 degrees. Let's see how far we're off. Well, if we're at the North Pole or the equator, we certainly can find our position. But at my office on the 45th parallel, Trish, my practice manager, is going to be pissed when I call her from the shores of Hudson Bay. Now, I'm sorry, I just have to listen to Phuket Word stumble about for a little longer.
So we have our latitude lines and a vertical line representing where Polaris should be somewhere above here.
Somewhere? You said it was at 3,112.3 miles, Phuket. Somewhere is pretty general. You nailed it to 1/10 of a mile.
We should get something like this. 10, 20, 30, 40, 5 degrees. These are the results that we get when we draw a line that is an angle equal to the latitude. Every 5 degrees of latitude, we get this wonderful curve.
Would somebody that actually passed middle school math explain to Phuket why you get this lovely curve? Or maybe did a string sculpture?
We don't have a dome either. Our dome is this curve of perspective, okay? So what we are talking about here for a flat Earth model is a flat surface, and the sun, moon, and stars all in layers that are parallel to the surface. And it's only because of the observations that we make in the sky that create this appearance of a curve or a dome. So when we talk about a dome, it's a dome of perspective. Okay? Yeah? A semi-sphere, if you like. But this sphere, or the dome, is one of perspective. So everything is parallel lines. It's like the flat Earth is like a sandwich. We're in the middle of a sandwich.
A sandwich. We're on a sandwich on a flat Earth. Okay.
I really hope that makes sense. And so there should be no need for anyone to argue that the globe is a fact. The globe is just an abstract mathematical interpretation of the observations that we have made of stars and celestial objects.
And perspective. Don't forget perspective.
Lines of latitude that are drawn and turned into a globe Earth work perfectly fine on the flat Earth when you factor in perspective.
No, Phuket, it really doesn't. It doesn't work with a triangle. It doesn't work with perspective. And quite frankly, this is simply an argument from ignorance. You have no idea what you're talking about, and you're making it up as you go along. Now, normally, when I do a debunk of a flat Earth video, I at least show the flat Earth scientists some respect for an effort. Can't really do that with you, Neil. It's like you're not really even trying, and you're just kind of throwing stuff up and seeing whether or not, if you say perspective and horizon rising to eye level and just these buzzwords, that somehow it'll all be okay. Well, it won't, sir. Unfortunately, you sound like a nice guy, but when it comes to science, you're a hack. If you want to change my opinion of you, then let's go ahead and do something that might actually have some merit. You haven't said anything about atmospheric lensing bending the rays of the sextant from Polaris to maybe explain some of this. So why don't you try that? Now, mind you, I didn't say it was going to be easy. If you're going to try and claim that this is atmospheric lensing, you're going to have to account for all of these different refractive indexes, which vary by degree of latitude. And then in order to claim that there must be a lens up there, you don't necessarily have to show me the lens, but you're going to have to show me exactly how you're going to calculate the curve on that lens. Here, let me help you out. There you go. There's the equation to do it. Why don't you go ahead and calculate the lens required to correct the light of Polaris at the equator, 15, 30, 45, 60, 75, and 90 degrees. Should be easy, especially for a super smart guy like you that actually redefined a new field of perspective. Good news, I'm still going to do another video on you and outline your new science of silly pseudo flat earth perspective, or whatever you want to call it. Until then, this is Bob Townsend signing out from Northern Michigan. Thanks for listening.